Hello, everybody. I hope that I'm audible. I hope the sound is okay. I hope the visuals are also okay. All right, I'm just going to give it a minute or two just for more people to join us. And we are going to start in just a minute. But good evening to everybody. And once again, we are back together. Thank you so much for joining us. And I hope that I'm audible. Otherwise, you can just hit me up on the comments and let me know if I am perfectly audible. Today, I thought that we would just take a walk through the May-June 2024 exam. All right, it has some really pretty interesting questions. Now, guys, what I am going to do is the last time we did a live on paper 2, I think we took a lot of time on trigonometry. So perhaps maybe go and watch that one, for some knowledge on trig. If we do have enough time, I will go back to trigonometry. Okay, I've got my daughter here with me, Umelo. So now and then I'll need to take care of her just to make sure that she's okay. But what I am going to do is I'm going to start with Euclidean geometry, all right, so that I can walk you through properly on that one. I think quite a number of people, when we asked and surveyed, said that they'd like for us to go through Euclidean geometry. And then what I'll do is that perhaps when we've got enough time, maybe I'll look at the trig graph. I'll also look at some proving of identities and so on, if we do have enough time. But all right, I hope that everyone is nicely seated and you are ready. For those of you that will be writing tomorrow, I want to wish you all of God's best. And I hope that this live will be able to assist you. And guys, we will be continuing with these lives. So we've got lives for memberships only, that only run on Mondays and Wednesdays. That's on maths for Mondays, and that's for physical science. However, if we do miss a day, we will actually make it up on one of the days. So those I will run directly from my class. Actually, this is at the center, which is in Honeydew. All right, and please, if you need some more information, if you need to have any of our services, you are more than welcome to get in touch with us. Our email address is info@mlungisinkosi.co.za. Let's pray good to that voice does behave throughout the lesson. All right, now let's get right into it. I'm going to start with question 8, right? And this is quite a popular question. They say to us in the diagram, we've got chord AB, we've got BC and AC, which is drawn in the circle with center O, and BCE is a tangent to the circle at C. Now they want us to prove the theorem which states that the angle between the tangent of a circle and the chord drawn from the point of contact is equal to the angle in the alternative segments. Hey, nah man, these theorems sound really difficult when you actually state them as they are. But essentially they want us to prove the tan-chord theorem. Now, firstly, what are we required to prove? We are required to prove that angle BCE, which is this angle over here, is equal to angle A, which is the angle over there. So what do we do? The first thing required to prove, firstly, is that angle BCE is equal to angle A. Right, so firstly what we are going to do is construct there a diameter. Okay, remember that a diameter is a line that passes through the center. Okay, I'm going to draw my diameter there. It's really misbehaving, but there it is. So I'm going to draw diameter BOP. If you don't mind, I'm just going to call the other point there P, right? And what you also do is you draw chord PB, right? So I'm going to draw chord PB. So these are my construction lines. So let's write there, construct. Okay, firstly, diameter. So I'm going to draw my diameter there, POC, and chord PB. Okay, chord PB. Right. Now let's get right into it then. Right. So firstly, what do we note with this theorem? Right. So firstly, what we note is that we know that PBC, so angle PBC, is equal to 90 degrees, right? And why is that? We know this is the angle at semicircle, right? So this is the same angle at semicircle. So we know this guy here is 90 degrees, right? Now, if in this case, now I want you to please note, if we know the angle, oh, by the way, we also know that angle PCE is also equal to 90 degrees. But why is that? This is the tan perpendicular to radius theorem, right? So we are going to say, well, we know because the tangent is perpendicular to the radius. Okay, so we've established both of these angles are 90 degrees. Now, we know the angle, let's call it angle C1, or you can say PCB, right? So angle C1, okay? Now, if we wanted to find C1, let's call it X, right? So let's call angle C1 X. So let angle C1 equal to X. Then what happens? Then we can actually find out what is the angle, right? What is angle P? So angle P, right, in triangle PBC, so in triangle PBC, right, we know that angle PBC, or let's rather call it angle P, plus angle PBC rather, which is that 90 degree there. We've just established that that is 90 degrees, plus C1, these are equal to 180. These are sum of angles in a triangle. Angles in a triangle. Now, what does that mean? It means that angle P, right, will simply be equal to 90 minus X. Now note, what am I doing? I'm working inside this triangle over here, and I've found out that this angle here, because of the angles on a triangle, this angle here will be equal to 90 minus X. But what do we know? We know that angle P will be equal to angle A. These are angles on a same segment. So this angle here is going to be 90 minus X as well. So that's equal to 90 minus X. Okay, these are angles on the same segment. Okay, finally, let's bring this to a landing. So in this case, we've already established that PCE, which is that angle over there, is also, oops, I just erased that by mistake. We've also established that this angle over here is 90 degrees. So in this case, that means if I were to call this C1, or in this case we called it BCE. So BCE plus angle C1, or you can say angle PCB, those are equal to 90 degrees, but we did say that this is because of the tan perpendicular to radius. So therefore, in this case, it means that angle BCE will be equal to 90 minus X as well. So remember, if we add them together, they give us 90. But C1 is equal to X, so that will be equal to 90 minus X. And therefore, what have we proven? We've been able to prove that angle BCE is equal to our angle A in this case, and both of them are equal to 90 minus X. And that's how the cookie crumbles, ladies and gents. That's how we prove the angle, the tan-chord theorem. Okay, right. You just need those two construction lines. There is another way, but for the sake of time, ladies and gents, please allow me not to use that one. This is really going to land you safely. All right, now let's go on to the next part. So 8.2, they say to us in the diagram, PQRS is a cyclic quad, okay, cyclic quadrilateral, and they tell us that RQ is equal to RS. Now please guys, as soon as you've got lines that are equal, firstly indicate if it's not in the diagram, right? But what does that help me with? It automatically means that a triangle RSQ is therefore an isosceles triangle, right? So what does that mean? It means that Q1 must be equal to S2. Those are angles, right? Opposite equal sides, right? So as soon as you've got those equal sides, sometimes even when they give you radii, right, to be equal, you know radii are equal. So as a result, it means that now you can take that angle, you know, angles opposite equal side and make them equal, right? But we're not there as yet, okay? Sorry, it does seem like I'm gonna have to keep hydrating. Okay, so now let's go for it. So they say ST is a tangent. Now guys, when you've got a tangent, of course, we're going to look for the tan-chord theorem, okay? And as well as, so already, if I were to use tan-chord, there's my tangent, there's my chord, right? The angle opposite that chord is actually Q1. So that means that if I look at T1, T1 would be equal to Q1. Okay, right, let's go for it. And they say SR produced, ST rather is a tangent to the circle at S, and SR is produced to N. Now remember, once they tell you that a line is produced, what they simply mean is that that's going to be a straight line. So look out for that. And what that will help you with is that it will tell you, firstly, you might have exterior angle of a triangle. Secondly, you might have an exterior angle of a cyclic quad. Thirdly, what you may have are, in fact, you might even have angles on a straight line, right? So in this case, we know that if it is produced, then it's going to make a straight line. Now, already what I can see there is that that's going to be an exterior angle of a cyclic quad. Remember, they told us that PQRS is a cyclic quad, but even if they didn't tell us, we know it is a cyclic quad because the vertices all touch the circumference of our circle. So R2 should be equal to angle P. So that's going to be 68 over there. Right, now guys, let's go for it. Let's go for it. Okay, so they say to us, determine with reasons the size of angle P. Now we've just done that. So angle P will be equal to angle R2, right, which is 68 degrees. And why is that? That's the exterior angle of a cyclic quad. Exterior angle of a cyclic quad. Okay, right. Of course, you can write out the cyclic quad in full. All right, nothing wrong with that. And then they say to us we must work out what angle Q1 is. Now, if you remember what I had already said in that case, right? If you note there, first of all, I note that angle R2 is an exterior angle to triangle SRQ. And in this case, we know that the exterior angle of a triangle is equal to the sum of the opposite interior angle. So, which means R1, let's rather say which triangle we are working on. In triangle SRQ, right? I know that R2 is equal to S2 plus Q1, right? So that's the exterior angle of a triangle. So exterior angle of a triangle. But what do we note? But we know that angle S2 is equal to Q1. All right? And in this case, remember, because we've got those two sides equal, right? We can say these are angles opposite equal sides. All right? And we can state the sides that are equal because SR is equal to RQ. Okay? So those are angles opposite equal sides. Now note, guys, those two angles are equal, right? And the exterior angle is equal to the sum of the opposite interior angle. So which means that both S2 would be equal to Q1, right? Which would be equal to 68 divided by 2. Remember, S2 plus Q1 are equal to 68, which is R2. And so in this case, because they are equal, it means that their magnitude will each be 34 degrees. So I've got this guy as 34, and I've got this guy to be 34 degrees, right, which is going to give us 68. All right, so Q1 is 34 degrees. Right, now S1, how do I find the value of S1? You remember that tan-chord theorem, right? So I said in this case, there's our tangent, there's our chord, right? There's our chord, sorry. So there's our chord. In this case, the angle between the tangent and the chord is equal to the angle on the opposite side of that chord, right? So in this case, it means that S1 will simply be equal to Q1, which is 34 degrees. And all that there is that we've got the tan-chord theorem. Okay, right, and that's how the cookie crumbles on that question. And guys, note, just these two questions alone, you would have earned yourself 11 marks. Euclidean geometry is quite feasible for you to do and get right. Okay, so let's go on to the next question, right? Now, I don't know about you, but I do prefer the questions on Euclidean geometry that more or less have to do with, you know, calculating angles as opposed to the just abstract questions, right? Those are easier to navigate. Now, let's look at the next question. They say in the diagram we've got AB, which is a diameter. Now, the moment they give us a diameter, okay, I am going to look for my angles at semicircle. But you also have, it passes through the center, right? They say center to the circle with center F, right? So F is the center. Now, again, the moment that you've got a center, please look for your radii. So that means FC should be equal to DF, should be equal to FA. This should be equal to BF as well. All of those are your radii. Why is that important? Because automatically, if you look at this angle, for instance, D3 should be equal to A1 because that's an isosceles triangle, right? Angles opposite equal sides. But also, if you look at that, I've got A2 equal to C2. Those are also angles opposite equal sides. And also what I do have in a different color there, all right? So I want you to note, in this case, D2 should be equal to C1. Again, angles opposite equal sides. In this case, you've got an isosceles triangle in DCF, okay? Right, now, they say to us, determine giving reasons. Any other angles, oh, no, I didn't finish reading the statement. They said, A, B, and CD intersect at G, all right? They are telling us what we know. FD and FC are drawn, okay? And BA bisects. Now note, in this case, they said BA, so it bisects CAD. So this angle here, CAD, is bisected. What does that mean? It means that A1 will be equal to A2, okay? Please, I want you to note that. I'm going to write that down somewhere so that I remember it. So A1 should be equal to A2. right? I am told that that angle BA, or rather side BA, bisects. All right, now they say to us, determine giving reasons any other angles, any three other angles equal to D1. All right, now let's go for it, ladies and gents. Let's go for it. Let's go for it. Let's see. So D1 is 37 degrees. All right. Now that means that A2 should also be equal to 37 degrees. Our bow tie theorem, right? Our bow tie theorem. In this case, these are angles on the same segment. Okay. So D1 will be equal to A2. A2, and that's equal to 37 degrees. But we also know that A2 is equals to A1. So let's start with that one. D1 is equal to A2, equal to 37 degrees. These are angles on the same segment. Okay. And then also we know that A1 is equal to A2, isn't it? So therefore it's equal to D1. A1 is equal to A2. That's also going to be equal to 37 degrees. And that was given. Okay. Right. Any other angle that is equal to 37. Now we know this guy is 37 degrees. So that also means that C2, right? Remember, as I said to you, so C2 is going to be equal to A2. In fact, firstly, we need to declare that those are radii, but we know that FA is equal to FC. These are radii. And I know, guys, in my class very recently, they said, sometimes they pronounce it radii. Okay, no. It's actually radii because that's plural for radius. So one radius, it's many radii. Okay, right. So FA is equals to FC. So therefore, it means that A2 is equal to C2. That's also equal to 37 degrees. Why is that? Because these are angles, opposite, equal sides. Okay. And then also, okay, just a bonus one. Because we found A1 to be equal to, so that's 37 as well. But A1 is also equal to D3, isn't it? So A1 is equal to D3. I know they had only said 3. We've already found our 3. But I was just adding this one. So A1 is equals to D3 because in this case, those are angles opposite equal sides. I should have also declared my radii as well, right? Which is 37, okay? And these are angles opposite equal sides. All right. Okay, guys, I hope that is clear to all of you. Now, in the next question, they say, show that DG is equal to GC. So, they say, show that DG, so this guy here, this line here, is equal to GC. All right. I'm sure many of you are already thinking theorem 1, right? If we can prove, now I want you to please note, if we can prove that either G1 or G2 is actually 90 degrees, then we can actually prove that that is equal to, or rather that the line drawn from the center perpendicular to the chord, it therefore bisects the chord. All right. Now, how can we do that? So what I'm going to do, I already found this guy to be 37 degrees, right? So using angle at center is twice angle at circumference. Okay, angle at center equals twice angle at circumference, will give me this angle over there. Okay, let me see where I want to go with that. Yeah, no, actually, I can find this angle over here. In fact, I don't even need to go angle at center. I can find this angle over here. Now remember, what do I note? Angle BDA, right? So BDA is equal to 90 degrees. Why is that? This is the angle at semicircle, right? So angle at semicircle, right? And I know some of you guys want to Americanize this. You want to say semicircle. That's okay with me. You can pronounce it that way. So in this case, I want you to know that composes of angle D1, D2, and D3. So that means that angle D1 plus D2 would be equal to 90. Angle D2 plus D3, right? So these two angles over here, right? D2 plus D3 are 90 minus 37. So that's 90 minus D1. And so in this case, our 90 minus 37, that's going to be 53 degrees. Okay? Right. So in this case, that those two give us 53 degrees. So I'm looking at these two angles over here. So they give us 53. Now, would we be able to get angle G1 in that case? I'm going to go in triangle DGA, right? So in triangle DGA, right, sum of angles on a triangle. So I'm going to take D2 plus D3 plus, please show the angles, guys, plus angle G1 plus angle A1. This is equal to 180. That's sum of angles in a triangle. Okay? Right, we said D2 plus D3 is 53 degrees. G1 is unknown, that's the one that we want. But we did say that A1 is 37 degrees. And this is 180. So that means that G1 is equal to 90 degrees. And there it is. We've proven that G1 is equal to 90. And so, what do we note? Therefore, DG is equal to GC. But why is that? This is line from center. Line from center. Perpendicular to the chord. We know that a line that is drawn from the center that is perpendicular to the chord bisects that chord. And so therefore, DG is equal to GC. Now, let's go for the last one. They say if it is further given that the radius of the circle is 20 units, okay, so the radius is 20 units, they said calculate the length of BG. All right, so what are we looking for? We are looking for this length over here, right? All right, ladies and gents, let's see. Maybe let me calculate. Let's see. What can I get over there? Calculate the length of BG. Right. So let me do this. So I know what the length of this entire guy is. So if the radius is 20, so BA would be equal to 20 times 2, and that is 40, right? Is there a way in which I can find what AG is? I definitely can. So I'm going to go in triangle. So in triangle BDA. BDA. Right? Now, please, I want you to note, ladies and gents, we found out that this angle here is 37 degrees, right? I want to find the angle that is adjacent, which is side GA. So that's a 90-degree triangle. So I know that GA would be adjacent to this angle, right? So it would be adjacent to that angle. But what other side in this case would I be able to obtain? So I want you guys to please note, we could have actually found out what is that side over there. Okay, I do think that there might be an easier way to do that. I think there might be an easier way. Let me see. Yeah, in fact, if we used this smaller circle, this smaller triangle over here, right? What do we note? So, if you remember, we were able to find, now in this case, this angle is 37 degrees, right? And I know in this case, if that's 37, and that's 90, the whole angle is 90 degrees, I can find angle D2, right? In fact, I can find angle D2. So I know D1 plus D2 plus D3 is equal to 90 degrees. And so what does that mean? It means that I can find angle D2, right? That's 90 degrees. And so D2, let's see quickly, that's 90 minus 37 times 2. That gives me 16 degrees. And I'll show you why I want to find that side. Nah? Right, so I've got this angle over here, all right, if I can show you. Right, D2 is 16 degrees. And how will that help me? It will help me to find angle or side FG, right? So I can say in triangle DGF. Okay, so that's 16 degrees. So in triangle DGF, right? So note I'm working on that triangle. I want you guys to be able to see it. I can say, well, I want the opposite side, and I've got the hypotenuse. Now remember that the radius, DF, is the hypotenuse, right? I mean, the radius is the hypotenuse. So I'm going to say the sine of angle D2 is equal to the opposite, which is DF, divided by the hypotenuse, which is, the opposite is not DF, the opposite is GF. Yeah, so that's GF, divided by the hypotenuse, which is DF. Okay, so that's DF. Now remember, what are we looking for? We are looking for GF. So in this case, GF will be DF, which is 20, the sine of 16 degrees. Now I'm going to leave it in that format, right? So I have now found, let me go into my diagram. I have found the length of this side. Okay, let me show it to you. I found the length of this side, which is GF. But what am I looking for? I'm looking for BG. But remember, BF is a radius, and it's given to me as 20. So BG plus GF. So BG, let's use a different color. So BG plus GF, this is equal to 20, right? So in this case, BG would be equal to 20 minus 20, the sine of 16 degrees. And of course, we can round it off to whatever it is. So 20 minus 20 sine of 16, all right, and I get a value of 14.49, okay, units, right? So that's the value of BG. All right, so I did that using, I'm sure there are various other ways in which you could have answered that question, but in my case, I used the smaller triangle, which is DGF. All right, so at the moment, ladies and gents, I'm not able to go and view your questions. Maybe I'll go back to my screen, my YouTube, just to go and check if there are any questions that are there. All right, so that I can be able to see those questions. Okay, right. In fact, maybe let me do exactly that. Let's see. Usine 16 ungenapi. Usine 16 ungena from the triangle. Remember, guys, I said in the triangle, the smaller triangle that I had just. If you can go to your diagram, right? You'll see. Let me just go back to it. I had gone into triangle. Right. Maybe let me maximize it a bit. So I went into this triangle here. Okay. I went into this triangle here. And remember, we had already found this guy to be 37. That one is 37. So that meant that this angle inside here is 16 degrees, right? Because the entire angle is 90. And so as a result, remember, this is the opposite side, UFG, right? And you've got the hypotenuse, which is DF. Remember, DF is 20 units, right? And so what I found was this smaller side, which is GF. And so after finding that side, then I subtracted it. Remember, this guy is a radius, and it's 20 units. So as a result, I said 20 minus that smaller side, which is GF, and I got the side BG. I hope that makes sense. I hope that, yeah, it does make sense. Okay. Right, now let's go on to the next question, guys, because I want us to run. Yes, that is on proportionality theorem, right? So firstly, guys, can I say this when it comes to proportionality theorem? Nah? You know, when you're doing questions on the proportionality theorem, sometimes the diagrams themselves can look very intimidating, but I can tell you this. You know, the more complex a geometric diagram can be, the more angles you are able to play around with, right? Secondly, if you know that this section is really not your strongest, my advice to you is, of course, I mean, it's the last question anyhow, right? So answer this question at the very end, okay? So that you don't get to break down your confidence. As I take some water, right, so that you don't break down your confidence, okay, on it. But I want us to go through this. So firstly, it's important for you to be able to prove similar triangles. Once you prove similar triangles, then you use proportionality, right? And what do? You know, this side over that side is equal to that side over that side, and then look for something that is common, okay? Right, so usually it works out better when you do it that way. Now let's go into the diagram. They say to us, in the diagram, COD is the diameter. So quickly, my diameter simply means I will be able to find angles that are equal to 90 degrees. So already I can already see this guy should be equal to 90 degrees, right? F2 and F3, 90 degrees. But it also means that B1 and B2 are also equal to 90. That's angles on a semicircle. That's equal to 90. And they also tell us that EA is a tangent to the circle at F. Right, so there's our tangent over there. So automatically that means that There is a tan-chord theorem that we can apply. Let's see, also tan perpendicular to radius. So if I look at this, angle F4 should be equal to angle C2. Okay, so those two should be equal, right? That's the tan-chord theorem. All right, let's see. Okay, yeah, let's continue. And then they say to us, we've got AO, which is perpendicular to CE. So AO, perpendicular to CE. All right, so they are telling us that that's 90 degrees. Okay, perhaps it will be useful later. And please don't make the mistake of applying theorem 1 here, right? But we do know those are radii, so these would be equal. So OC, OD, as well as OB would be equal, as well as OF, that would be equal, right? All of them are radii. All right, now they say COD produced intersects the tangent of the circle at E. Right, once they say produced, I did say to you that in this case they are just telling you that it is a straight line. So, all right, produced intersects the circle at A. CF intersects OB in T, and CB, BD, OF, and FD are drawn. All right, now guys, let's try and go into the diagram, and please let's be slow about it, so that you can be able to understand. I'll go back and see if there are any questions in that regard. All right, but I love the fact that you are able to help one another as well. Now they say to us, prove with reasons that TODF is a cyclic quad. So TODF is a cyclic quad. So what I want you guys to note is that once we prove something to be a cyclic quad, right? So we need to use all the properties of the cyclic quad to try and prove it. But once we prove that it is a cyclic quad, then in the subsequent questions, we can use it as a cyclic quad, right? So I can already see where that is going, because look at that. The exterior angle, O1, is equal to the interior opposite angle, right? Those are the properties of a cyclic quad. So I will say, well, O1 is equal to 90 degrees. That's given. Okay. Angle F2 plus F3 is equal to 90 degrees. All right. That's angle on a semicircle, right? So angle at semicircle. So angle at semicircle. Right. So that's the angle at semicircle. So in that case, what does that mean? Well, O1 is therefore equal to F2 plus F3. In this case, both of them are equal to 90. Therefore, TODF is a cyclic quad. Why? Because in this case, the converse of the exterior angle of a cyclic quad. Note, we are applying that that theorem in reverse, right? So in this case, we've identified that guy as a cyclic quad. All right. Now let's go to the next one. They say prove D3 equal to T1. I want you guys to note, even before we get to the proportionality part, we've already now been able to, just use normal Euclidean geometry, right? So they say prove D3 equal to T1. Okay, where is D3? So D3 equal to T1. Well, in this case, I hope you can see that it's actually from our cyclic quad, because D3 should be equal to T3. That's exterior angle of a cyclic quad. So because we've proven that guy to be a cyclic quad, then it means that that angle D3 is equal to T3. So in this case, I'm just simply going to say for 10.2, right, angle D3 is equal to angle T3. But why is that? Because exterior angle of a cyclic quad. Okay? And then, what do I note? But I know that T3 is equal to T1. These are vertically opposite angles. And so what does that mean? It means, therefore, T1 is equal to D3. All right, so we've noted those two are equal to each other. Right, we've been able to prove that. Now, they say to us, we need to prove that triangle TFO, all right, TFO is this triangle over here. Right, let me do this so that we can see it. This triangle over here, right? They say we must prove that it's similar to triangle DFE. DFE. Okay, so it's this angle over here. Right, I think we are almost there. We've been able to prove that D3 is equal to T3, right? We are already there. And let's see. Oh yeah. Let's see, which other angle? Let's see. Okay, you know what I'm going to do? Let me call angle F4X, right? You know, this is one of those abstract questions, right? So if I call angle F4X, that means that also angle C2 rather would be equal to X, right? Remember, these are angles, what do we call them? These are angles opposite, that's the tan-chord theorem. So F4 is equal to C2. That's the tan-chord theorem. Okay, let's see. Oh yeah, actually, so that makes this would be 90 minus X. All right, so that means T4 should be 90 minus X, meaning that T3 should be 90 plus X if we take the sum of angles on a straight line, right? I'm trying to see if we can prove, let's see. So if I take, so that would be X over there, right? So I'm trying to actually get another angle that would be equal to, so which means this guy is 90 plus X as well. We've already found it to be 90 plus X, right? Now, in this case, I've got 90 plus X over there. Oh yeah. In fact, rather, let's do it like this, right? So that means angle O3 should be equal to 2x. Now note, we've got angle at center, so they're both subtended by line DF. So this guy should be equal to 2x. And so, remember, angle at center, if this guy is x, then the angle at the circumference should be equal to 2x. Okay, so that should make it possible for us to now work out angle O2. Okay, so O1 plus O2, O1 plus O2 plus O3 should be equal to 180. Okay, I'm still going to write all of it properly, right? So that I show you how I got to that. So O1 plus O2 plus O3 should be equal to, our O1 is 90, that was given. O2 is unknown, that's the one we want. O3 is 2x, and that's equal to 180. And so I want you guys to please note in this case that that means that angle O2 will be equal to 90 minus 2x. Okay? Now, if this guy is 90 minus 2x, can we find angle F2? Right? So we go into triangle OTF. Right? So OTF in triangle OTF. Then I note, I'm sure there maybe is another way that we could have done this a little bit more easier. Yeah, in fact, now that I look at it, there was another way, but nonetheless, I've already committed to this one. For me to do that would only be complicating things. So now to find O2, to find F2 rather, F2 plus O2 plus T3, that would be equal to 180. So that means I've got 90 plus x plus I've got O2, which is 90 minus 2x. That's equal to 180. And so I hope that you guys can be able to see this, right? That, that's F2. Okay. That angle F2 would now actually be equal to x. So angle F2 would be equal to x. And so that means, in this case, this guy is equal to x, that guy is equal to x, and so we've got two angles that are actually exactly the same, right? Okay, right. Now let me go back into it, right? Let me go back into it so that you can be able to follow in what I did. Okay, I'm going to remove it. I'm sure many of you are actually complaining right now. Okay, right. So let's make it easier. I started with F4 and I said, look, what if we called this angle here x, right? Note. Then it means that angle C2 is equal to x. So F4 is equal to C2, which is equal to x, right? Now, what does that mean? It meant that angle, if I look at, actually, even much simpler, right? That meant that this angle over here becomes 90 minus x, right? So I am inside the angle, the triangle now. So that means T3, I forgot to write the reason for F4 and F2 and C2. That's going to be the tan-chord theorem. Okay? So we said T3, right, becomes the exterior angle of that triangle. And remember, the exterior angle is equal to the sum of the interior opposite angles. So T3 will be equal to C2 plus O1. That's the exterior angle of a triangle. So T3 will equal to 90 plus x. So what I've said is that this guy here is 90 plus x. But remember, what did we find? We found that D3 is equal to T3, right? So D3 is also equal to 90 plus X. Now guys, all that I'm going to do is I am now going to try and go into my triangle once again, right? So what did I do in this case? I said, look, I've got this side equal to X. Is it possible for me to find another angle within that triangle that is equal to, that would have the same? So I already have two angles that are equal, right? D3 and T3. How can I find another angle, right? I said, look, what if we found, in fact, we could have also used our cyclic quad in that case, but what if I can find the angle O2, right? But I know that O3 is equal to 2 times C2. And so that will be equal to 2x. And so I went into this angle here. I said this angle here is 2x. All right? I hope that is clear, ladies and gents. Right. Now, I want you to note, in this case, because this guy here is 2x, I know that when I look at angle E, if I take the sum of angles on a triangle, so O3 is equal to 2x. Okay. So if I take sum of angles in a triangle, in fact, let me just conclude with what I wanted to do. So the angle O2, which is in here, right? So the angle O2 plus O1 plus O3, this is equal to 180. That's sum of angles on a straight line, right? Sum of angles on a straight line. So I'm trying to find O2. So O2 is equal to 180 minus 90 minus 2x, right? So 180 minus 90 minus this 2x. What does that give me? It gives me 90 minus 2x. Now I found the angle O2 to be 90 minus 2x, okay? But if I go to triangle, in triangle DFE, right? Then what do I note? To find angle E, again, it's going to be angle D3 plus F4 plus angle E. These are equal to 180. Those are angles, sum of angles in a triangle, right? Now, guys, I promise you, after this, it gets easier, right? So, in this case, D3, remember we found that to be 90 plus X. F4, that is X, and plus E, and this is equal to 180. What do you note? Angle E will be equal to 90 minus 2x, which is exactly equal to angle O2. So now, notice guys, we've found two angles that are equal, right? So we've found two angles equal. This one is 90 this one is 90 plus x, that's D3, which was equal to T3, right? We found angle E equal to O2, both of them are 90 minus 2x, so O2 is equal to angle E. All you need to do when you want to prove similarity is you need two angles. The third one automatically becomes equal. So I can therefore say, therefore triangle TFO is similar to triangle DFE. Now guys, you've proved angles similar, right? Triangle similar, which means their sides would be proportional, isn't it? So perhaps they might want us to use this in another context. But they said if B2 is equal to E, prove that DB is parallel to EA. Okay, they said if B2 is equal to E, okay, so if E is equal to B2, which is this guy over here, right, prove that those sides are parallel. Now I want you to note OD is equal to OB, they are radii, and so B2 is equal to D1. Okay, so let's start there. So OB is equal to OD, right? And we said they are radii, and so therefore we know that D1 is equal to B2. D1 is equal to B2, right? But now, what do we note in this case? We know that D1 is equal to B2. These two are equal. But they told me just now that D1 is also equal to E. So therefore, it means that B2 must therefore be equal to angle E. In fact, I should have written there that B1 is equal to E. That's given. Okay. So B1 is equal to E. That is given. And so therefore, it means that B2 is equal to E. Why? Because both of them are actually equal to B1. So therefore, those are equal. So because they are equal, note in this case, D1 being equal to E makes those corresponding angles, right? So I should have said B1 is equal to E. So therefore, it means that DB is parallel to EA. Corresponding angles are equal. All right. So we've proved those sides equal. We've proved them parallel to each other. All right. And finally, guys, they want us to prove that entire thing. Where you actually start should be on your similarity. Right? So what I'm going to do is, they say prove that entire thing. Let's start with the similarity. So remember TF over DF. So let's write that down. TF, so TF over DF would be equal to FO over FE. And this would be equal to TO over DE. Right, and why is that? Because of the proportionality theorem, right? So what did they ask me to prove? They asked me to prove DO equal to TOFE over AB. Now already in my proportionality, I can see I've got TO, there's TO over there, right? I also have FE, there's FE over there. So I'm going to take those two ratios and I'm going to cross multiply them. So that means that FO multiplied by DE is equal to, so we cross multiply, TO multiplied by FE. Now already can you see that I've got my numerator over there, right? So what you then will go and do, ladies and gents, look for sides that are either similar or that are proportional, okay? So let's see. Which side? Let's see, FO. Where is FO? Right, so FO, that's the radius, okay? Let's see. So FO and DO. Yeah, definitely equal. But we know that FO is equal to DO. That's radii. radii. Hey. Right, so I can replace FO with DO. So DO times DE is equal to TO times FE. Right. Now that I've done that, okay, which one is missing? So I've got the DO on the left-hand side. So the only thing that's missing is AB. So which means there must be some kind of a relationship between AB and DE. Right? Let's go and see. So if I go there and say AB and DE, they are definitely equal to each other. Why is that? We've proven that those lines are parallel, right? Which means their sides are proportional, right? If you don't mind, ladies and gents, I'm just going to remove some of the things there so that we can be able to see. But in this case, so in triangle OEA, I've got OD over DE, right? OD over DE equal to OB over BA. OB over BA. But I want you to guys to note, in this case, OD and OB are equal, right? But OD is equal to OB. So therefore, it means that DE should be equal to BA. And so, ladies and gents, there we've proven it, that therefore DO multiplied by BA will be equal to TO times FE. And all that is left for us to do is divide both sides by BA. And we've essentially proven it. As I said, guys, you know, this section can be a little bit frustrating, especially on this proof that I was trying to do. Please, if any of you know an easier way in which you could have gotten that, okay? But in proving those similarities, that was the bit of a frustrating part, but in essence, we ended up getting there nonetheless. Okay, right, ladies and gents, I think for the sake of our time, I know that perhaps some of you would prefer for me to go through this again. If you can, you'll watch it again. We'll save this live. Okay, so what we'll do is that we'll just go on now because there was a request as well on looking at particularly looking at this section of trigonometry. All right, let me get some water. Hey guys, on a Sunday, I'm working so hard. All right, so I want us to go into 3D trig, and what I'm going to do is perhaps as the next step, I'm going to do a trig graph, but that will be the last thing that I do with you guys. Okay, so they say to us, in the diagram, we've got BC and D, right, that lie in the same horizontal plane. Okay, they say ADC and ACB are equal to alpha, and DCB is theta, so they are telling you everything that you can see there. All right, and they say DC is K units, and DC is, BD is equals to BC. All right, now guys, I think some of you perhaps have a little bit of a challenge seeing things in 3D, right? I tried to work through with my class, my daily class, on how to work through a 3D trigonometry, right? And eventually, as people got used to working with 3D, they began to see the diagram. So I think sometimes also a matter of practice, but I know it can be more challenging to some than it is to others. So they say to us, prove that AD is equal to AC. So they want us to prove AD equal to AC. That's very easy for us to prove, because if you look at triangle ADC, and triangle ABC. Okay? Right, we've got, in both instances, they've got a side that is equal. They've got a 90 degree, and they also have a common side, right? So I know that, or it is given to us that DB is equal to BC. Okay, that's given. And we know that angle ABD is equal to ABC. ABC. Both of them are equal to 90. All right, and that's also given. And we know that side AB is common, right? Therefore, triangle ABD is similar, in fact is congruent, not similar, they are congruent, right? Is congruent to triangle ABC. All right, in fact we even had an angle that was equal there, and so what can we say? Because they are congruent triangles, therefore it means that AD must therefore be equal. Oh, by the way, this would be side angle side, ne? Angle side. Okay, right, so that's side angle side, and so therefore it means in this case, or we can say right angle side, okay, and in this case it simply means that AD should be equal to AC. All right, right, so we've proven them congruent. So they say that prove that BD is K over 2 cos theta. Now, ladies and gents, you always try to work from the triangle that has the most information, right? So which triangle would that be? Okay, right. Now, in this case, you can see they've got theta over there, right? So what am I going to try to do, right? I know I've got a common side, okay? They said BD, so which is this side over here, right? So that BD over there, right? I know that this is angle theta, which means this is also angle theta. Now note, which means this angle over here would be 180 minus 2 theta. So in triangle BDC, I know in this case that angle BDC is equal to angle BCD, right? Which is equal to theta. Why is that? These are angles opposite, equal sides. If you need to, you can state again that DB is equal to BC. All right? So now that means that angle B plus angle D plus angle C is 180. Those are angles, sum of angles in a triangle. Okay? So what does that tell us? Angle B, so I'm going to use the sine rule, right? I'm going to say BD, I needed to say angle B, therefore, is equal to 180 minus 2 theta, right? Remember, we did say those two angles are equal to theta. So now, what does that tell us? It tells us that side BD over the angle that is opposite that side, that's the sine rule. BD over the sine of the angle opposite that, okay? Sine of angle C is equal to, now remember we're already given a side K there, which is DC. So that's DC divided by the sine of 180, or rather let me say angle B. Right, and now let's work through it. So BD would be equal to, if we cross multiply, that would be DC, the sine of theta, right, divided by the sine of B, which is 180 minus 2 theta. Now, of course, you know this by now, ladies and gents, when we are working with trig. So DC is equal to K, that's sine theta. 180 minus 2 theta gives us a sine of 2 theta. That's in the second quadrant. So that gives us the sine of 2 theta. But what do we know? That in this case, we've got K over sine theta divided by 2 sine theta, the cos of theta. And so what happens? The sine theta cancels out with the sine theta. And so I'm left with K divided by 2, the cosine of theta. I hope that is clear, ladies and gents. So that is how we prove that BD is equal to K over 2, the cos of theta. Right, now they say to us, determine the area of triangle BCD in terms of K and a single trigonometric ratio, okay, of theta. So BCD. Right. So we are working with the area. Now remember, anytime I'm working with the area, I need two sides and an included angle, right? So let's see. The area of triangle BCD. All right, if you don't mind, I'm just going to work from this side over here. All right, hey guys, we are running out of time. I've got about 30 minutes to go. Not 30 minutes, rather. I've got about 10 minutes to go. So let's quickly go into that. So we've already found two sides. Now remember, we've proven that BD is K over cos theta. But it's actually the same as that side as well, K over cos theta. All right, so let's find two sides and an included angle. So I'm going to say the area of triangle BCD is a half of DC, right? So DC multiplied by DB, or BD, the sine of the included angle, which is sine of D. All right, so let's do that quickly. So DC, that's K. That's going to be DB. That's K over the cos of theta. The sine D is theta. So that will be equal to half K times K, that's K squared. That's sine theta divided by cos theta, that will be the tan of theta. Okay, so that is the area of triangle BCD. All right, guys, let's continue. Okay, I think this is quite an easy proof. Please, if you can look at it. Okay, I wanted us as the last thing that we do, rather to look at this trig graph over here. Right, so they say in the diagram, and I hope you don't mind, guys, the rest of the questions, please, you can look at it on your own. Okay, and you can watch the previous live that we did on trigonometry. I covered it extensively. So they say in the graph we've got f of x, which is x plus a, and g of x, which is sine of 2x, right? For the interval, x is an element of negative 180 to 180, right? the graphs intersect at N, there it is there, at P, there it is over there, and at Q, which is right there. Right, now they say to us, write down the period of F. Now note, guys, for the graph of F, the coefficient of our X value is 1. So meaning that the period for the sine graph, we always say 360 divided by the coefficient of X, or the coefficient of our angle, right? So that would be 360. Right, and say they say the amplitude of G. So the graph of G has got an amplitude, that's the coefficient of our trig ratio. That amplitude is 1. Okay, right, sometimes when you're not sure about that amplitude, okay, particularly if you've got a shifted graph, you say maximum value minus minimum value, and you divide that by 2. Okay, right, so that amplitude is equal to 1. Right, now they say write down the value of A. Now guys, there are two ways in which you could do that. So firstly, I noticed that this is a cos graph, right? Firstly, it's a cos graph that is shifted. Usually, a standard cos graph looks something like this. It would be 1 at 0, and it would look like this. But when I look at this graph, 1 is at 45 degrees. Can you see that, guys? So it would have been at 0 degrees. So what did they do? They took the cos graph, they shifted it 45 degrees to the right. So which means that our A value, right? Notice when I shift to the right, that's negative 45. That's minus 45. Another way that you could have done this is you could have actually substituted the value at P, that is f of 45 is equal to cos of 45 plus A. But what is it equal to? It's equal to 1. So you'll say 45 plus A. This is the arc cos of 1, which is equal to 0. And in this case, A is minus 45. So you can do that by actually substituting one of the points that you have. All right, quickly we run, guys. Now they say to us, calculate the values of K, right, the coordinates of N and Q, without the use of a calculator. Right. Now, guys, I want you to please note in this case. Okay, so they want us to determine the value of K in this case, right? Now, if you notice there, now there's different ways in which we can work that out. So what I'm going to do is I could have substituted the X value at N or the X value at Q. Now notice, this is going to be F of X, that's cos of X plus A. All right, now what's the X value at N? That's cos of negative 75 plus, remember we've already found out what the value of A is. We said that's minus 45, right? That's minus 45. But what is it equal to? This is equal to K. Now you'll notice that K, in this case, minus 75 minus 45, okay, in fact, I think it would have been even much better had I used. So that's 75 plus 45, right? So 75 plus 45, that's 120. So K is equal to the cos of minus 120. Now remember, when we apply our, our trig ratios, so cos of negative 120, okay, that would be in the third quadrant, okay, or you can say 360 minus 120, and in this case, it would be much easier to use that. You'd say 240, but what you end up with is minus the cos. In fact, maybe let me just show you that. So k is equal to the cos of 360 minus 120, which is cos of 240. But you can actually say this is the cos of 180 plus 60, right? You've got 180 plus 60, and so this would be minus the cosine of 60 degrees. Now you know this is a special angle, so which means that k would be equal to negative minus 1 over 2. Okay, right. You could have also used 165. You would have ended up with cos of 165 minus, actually I think that would have been even easier, 165 minus 45, and that would simply give you cos of 120, and again you'd say this is minus the cos of 60 degrees, and you get that to be negative 1 over 2. All right, so k is minus 1 over 2 using your special angles. Now, they say to you, calculate the values of x if g of x plus 60 is equal to f of x plus 60. Now, guys, they said between negative 45 and 0. Now, what exactly are they doing in this question? Firstly, I want you to always do this. So this is g of x and this is f of x. And what did they do? They shifted them, right, to the left by 60 degrees. Now let's find all the solutions where f of x is equal to g of x. We know that f of x is equal to g of x at negative 75, at 45, at 165. Right? So minus 165, 45, and at, minus 75 rather. Minus 75, 45, and at 165, right? Now, if I shift these solutions by 60 degrees, right? Now remember, plus 60 means I'm shifting them by 60 degrees to the left, right? So which means, in this case, that would be at, that would be minus 60, that would be minus 60, that would be minus 60 degrees, right? So what does this give me? Minus 1, hey, my brain is freezing now. Minus 135, minus 105 definitely doesn't qualify. This would be 165 minus 60. That would be, sorry guys, that's not minus 145, sorry. That's minus 15, right? 45 minus 60 gives me minus 15, okay? And this one gives me 105. But remember, they said between negative 45 and 0, so which means it's only this one that qualifies. So the correct answer there is x is equal to negative 15. So remember, you start where your graphs are equal, but then you go to, you shift that solution by whatever angle that they have shifted it by. All right, now finally, they say without the use of a calculator, determine the number of solutions. The equations root 2 sine of 2x equal to sine x plus cos x has in the interval minus 90 to 90. Clearly show all working. And remember, the operative word is without the use of a calculator. Now guys, I want you to always note, everything they ask under the graph is related to the graph. So we already have the graph of sine 2x, right? So what I need to do is take my solution. Sine 2x is equal to sine x plus cos x, okay, divided by root 2. Sorry, I'm rushing now for the sake of time. So this would be 1 over root 2 sine of x plus 1 over root 2. All right, even our battery is complaining now. 1 over root 2 Yeah, so that it doesn't switch off whilst we are busy. Let's do this. So that's 1 over root 2 cos of x. Now, I want you guys to note, this is related to the graphs that you actually have there, right? We already have that graph of sine of 2x, okay? Now, how do we change this to become like the graph that we have? That is the cos graph of x minus 45. Now, note, this is, you can say, this is cos 45 sine x plus sine 45 cos x. And what do you notice in this case? All that I can simply do, this is the equivalent of the cos graph, right? I will say this is x minus 45, right? When I use the, when I use, in this case, my compound angle formula, right? In this case, I get x minus 45. So essentially, what are they asking me? Where is the sine graph, this sine graph that's there, equal to the cos graph between negative 90 and 90? I go to my solution there. It is definitely at x is equal to 45. So therefore, our solution in that case is x is equal to 45 degrees. Ladies and gents, I am going to leave it there. I am just 1 minute over time. Okay? Please, guys, for those of you that are writing tomorrow, I've really tried my absolute best. I know that perhaps some of you still have some more questions, but I've got lots of videos on these sections. Please, guys, make it a point that you study as best as you possibly can. I'm trying to look at your yeah, let's see. They're saying, guys, don't sleep. No, guys, let's not do that. Let's not do that. Okay, right. So all I'm asking you is really to use the remainder of the time. If I were you, please try to sleep on time. We've got the paper for you to download if you need to download it. It's really been a pleasure to be with all of you. Please join in and become a member on this channel. I will be doing more and more of these as we continue, right? And please don't be afraid, guys, to support us as a channel. To keep us going, we have to make sure that we pay the bills and so on. So please, if you can contribute in any way, please, that would be much welcomed. Okay, right. I am exhausted this Sunday afternoon. Hey, I hope that you will write well. Wishing you all of God's best. And please do not be despondent. If you guys find yourself at that point where perhaps things are not working out as you'd like them to, I would definitely recommend that find a way for you to keep going. Ngesizulu bathi akulahlambeleko ngakufelwa, meaning that don't lose hope. Okay, don't lose hope. Even how dire the situation may be, I want you to know that God is on your side. Secondly, that you are not beyond any form of assistance. If you need assistance, reach out to us. For those of you that want to be part of our online sessions, you are welcome to also join in with that. Our information there. You can go on to info@mlungisinkosi.co.za. We've made it quite affordable as well. But yeah, we are definitely willing to assist you. Okay. I will see you guys again next time. Hopefully you will become a member and we'll see each other on a weekly basis, right? Twice a week. Mondays for maths and on Wednesdays for physical science. From me, guys, I will see you guys again next time. Shap shap.